好，應該係咪
Okay, so suppose you have a very good lunch. Now let's get back to work. We will have a afternoon section. Basically, Dr. Yip will be our main major speaker. First, he will talk about some fundamental that will be about AI and machine learning. That will be, I'm sure, very useful for your hackathon. Okay, and then he will prepare a workshop for you to get use some warm up on preparing the hackathon. Okay, so I will give the time to Dr. Yi.
Okay, thank you. Okay, so I think these things are not really important now, and so I guess I should start here. Okay. So yeah, this section is called the talk on fundamentals, but I find that it's not really that fundamental because I don't know how to think after listening to the briefing section in the morning. Okay, do you think the problem is difficult one or easy one? Or do you have an idea how to solve the problem? Or do you have an idea what the deliverable is? What the deliverable should look like? Okay, these seem to be in the cloud, right? And well, that requires quite a lot of our understanding between in meteorology and also machine learning and AI and stuff. And so I'll talk a little bit about how we can approach the problem, okay, and what kind of reporting and things can be done, and then do a little bit of workshop on one piece of data that has not been mentioned in the modeling section. So a little bit about myself, okay. I just call it Vita, and this is my email address, okay. And I think for this hackathon, okay, later we'll create teams for every group, and hopefully I'll be in this group as well. So if you have problems and you have questions, feel free to ask in the team groups, okay. Email, usually I respond really slowly, okay, because there are hundreds of emails every day. And well, I'm pretty sure that okay, it's but your collective wisdom is actually much better than mine. Okay, I'm not really used to this kind of screen casting. Okay, anyway, okay, I have to use this kind of stuff. Okay, but anyway, okay, so now let's to learn with you all. I'm sure that your collective wisdom is much greater than mine. Okay, all of you are expert in some areas that I'm not an expert with. Okay, the only thing I'm better than you in the sense is that I learned something earlier than you. So that's why I'm here. So now, well, most probably, okay, handling of meteorological data is something new to you. Okay, how many of you have experienced handling meteorological data in the past? Weather data? Yes, no, only one, two. Yeah, I heard that there are some interns, okay, in Hong Kong, all will participate in this hackathon. Okay, anyway, okay, I know who you are. But anyway, in a sense, okay, I'll be sure to explore because we are dealing with a data type that is essentially okay a completely new one to us, and there are a lot of things to learn. So I hope you can enjoy. Before any talk or course, okay, I usually give students some quotations. And the first one is that, okay, those who can't will do, okay, so you are the one who will be able to do the work of solving the problem, okay, to produce the deliverables, okay, and those who can't will teach, okay, and this is actually a quotation from George Bernard Shaw in one of his plays. And indeed, okay, how many of you have heard of this quotation? Yes, no, okay, if no, then if you have time, then try to find out, okay, what's another one that follow this one. Okay, it's called Mencken's expansion, okay, which I don't take the time to explain now. And the second quotation is that, okay, if you like everyone, you have low taste. And if everyone likes you, you have low character. And so I'm certainly not able to please all of you, okay, because as I have said, okay, most probably you are expert, more expert than me in some areas, and but I'm more expert or experienced in some area than you. So that's why I'm here. Okay, in the morning section, you have been introduced a number of background information about the data that you are going to handle. And if you have followed the link in the sheet, when you register and come in, you'll find that there are about 3 gigabytes of data on the Google Drive, or is it Google Drive or Live or something? Okay, and you'll be able to download. Okay, and these are the sample data. And these are only part of the data, and we have to have a look into the data, okay? Because as computer scientists, most probably we don't know what they are. So what are available to us include the ones from Hong Kong Observatory, and this is one of the images, and this image is the radar image, and this is what we call radar reflectivity image, and the reflectivity tells how strong a particular location, okay, or the reflection of the radar echo at a particular location is, which indirectly tells how strong the rain would be, okay. And notice that now, well, how can we know, okay, where or how strong or how much rain would there be, and what kind of data is it, okay? The thing that has not been told, communicated to you in this modeling is that radar data are data that are in the sky. Okay, the radar echoes are actually 3 kilometers above us. Okay, and so the first question is, okay, is it possible or is it reasonable to extrapolate that if 3 kilometers above me, there is a strong echo, okay, and all the clouds and things, okay, are moving westward. Okay, can we infer that? Okay, that echo, that very strong echo, would be giving me rain, okay, corresponding to that strength. Okay, the thing that we have to notice is that we are dealing with data 3 kilometers above us. And if you have looked at the sequence, you'll find that actually these rain bands and echoes move. And so this is one of the reasons why the Hong Kong Observatory suggests that when you do the hackathon results, okay, when you do the analysis, you have to do a little bit of prediction of what is the rainfall, okay, at a particular location a few minutes later, rather than inferring from the data directly at the moment. Okay. Also, it takes time for rain to fall from 3 kilometers down to ground level or sea level, even if there is no wind or no movement of that. Okay, so this is one of the things that we have to be careful about. And these are reflectivity images. And another thing that has not been mentioned in this modeling is that there are masses. Okay, if you have looked at the data, how many of you have looked into the data already? Yes, okay, so you find that there are some folders, okay? One is reflectivity, another is mask. And for every reflectivity image, there is a corresponding image for the mask. And the mask, of course, okay, tells you which pixel or which piece of data in the reflectivity image is valid and which one should not be considered. Okay, and this reflectivity, this mask data, okay, can actually be visualized, and this will become our workshop exercise a little bit later. Okay, this one is actually pretty interesting to look at. We are also given weather photos. Okay, and weather photos, something like this. Okay, and if we look at the file names, okay, you'll find that this is 1705 24. Okay, so it's 2017. Okay, the year, and it's May 24th, and the time is 10 o'clock. Okay, 36 minutes after 10 o'clock. Okay, and for this one is 35 minutes after 10 o'clock. Okay, and this one, okay, is the Hong Kong image. Looking at either east or west. Okay, can anyone recognize? I cannot. Okay, and this is one of the pair of Hong Kong images. And weather photos is taken by Hong Kong O, and we have to analyze it as well. Okay, the question is, how can this be related to some of the pixels in the reflectivity data, or is this kind of correlation or analysis useful? Since our goal is, at the end of the day, gauge how much effect weather will affect traffic flow. So we are getting transport department data. Okay, essentially these are the cams. Okay, this camera obviously is not as high in resolution as this one. Okay, and the good thing is that nearly always it looks at a row. And so we have to process them as well. And these are called traffic snapshots. So for those who have explored the data, okay, I think you already know what they are, right? So it seems to be pretty simple, okay, but it turns out to be not the case, at least to me. Okay, we have all these three kinds of data, but we need some metadata to know where the stations are. So for weather photo, okay, the metadata contains weather photo station key, the latitude, longitude, and also textual remark. All of them in an Excel file, which means that, okay, if you want to process, it's pretty easy. Okay, just export it as CSV or directly read it as an XLS, and you'll be able to get all the columns and things. Okay, so it's just a few lines of code. Okay, if you know which library to use. And the distribution is here. Okay, this is something that you have seen earlier today, and I'll tell you why this is important. Okay, a little bit later. We also have another set of metadata for the transport department. Okay, and the transport department, if you look at the points, okay, you'll find that the number of cameras is much more than the number of weather cameras we have in the data set. And this seems to be a good thing, okay? For each camera, it has the key, which is the camera ID, the region, whether it is in Kowloon or New Territories or something, and the description, textual description, and the location, okay? And the location is represented in two ways. The first way is the traditional latitude and longitude, which is something supposedly we already know. But another one is represented as easting and northing. Okay, and easting and northing are essentially geographic Cartesian coordinate. The idea is that when you draw a map, okay, you take the map as a rectangular piece of paper, and you cut that rectangular piece of paper into equal sized strips, okay, horizontally and vertically. And the count up and count down, count left, count right would be the eastings and northings. Okay, of course, as the name implies, easting goes east and west. Okay, northing goes north and south. Okay, this could differ very much from the calculations from latitude and longitude, especially in areas or in cities where the latitude is high. Okay, but in Hong Kong, okay, we are at 23 something, and it's still useful, okay, because we don't need to do the conversion between the latitude and longitude to the Cartesian coordinates. So we know all the data, okay, and the real question is, okay, what is the actual problem? Okay, actually up to this point, okay, do you have an idea what the problem is, okay, that you have to solve? Seems so, okay, at least we have been briefed. So we are given the time sequence, or given time sequences of weather reflectivity data and weather photo data, and and the traffic snapshots. And what we are going to do is to do rainfall prediction, which is one, and assess the impact of road traffic. So actually, the organizers are expecting two things. The first one is rainfall prediction. Okay, the second one is impact of road traffic. Okay, I'll go back to the briefing notes of the first section, and you know that. Okay, I just copied and pasted that line into this slide. And so rainfall prediction. Okay, and if you remember earlier in the briefing section in the morning, okay, there are many methods to find out how a bob of with activity would move from one place to another after 6 minutes, okay, by using methods like simple extrapolation or more complex is semi-Lagrangian affection methods and things like that, okay, optical flow methods and so on, okay. So most probably, at least for me, okay, I don't know before I do project related to these, okay, I don't know what all these are. Okay, I taught multimedia in Hong Kong U, okay, for some of those you may know, and there are methods for estimating the movement of objects, okay, and these are something very similar, okay, but for meteorological data, okay, the special thing is that essentially, okay, we are looking at a drop of water moving through the sky. Okay, and the blob of water moving through the sky, if it doesn't produce rain, then the blob of water, the total amount of blob of water would kind of preserve. But of course, okay, for those echoes, okay, strong enough to produce reflectivity, that can be converted into millimeters of rain, then essentially the blob of water, okay, would reduce in size. Okay, if there is no new water coming in. Okay, so that's why we have to use things like optical flow or special averaging methods, okay, to do the calculation. Okay, and so this is one of the possibilities. And so make these keywords to you. Okay, I mean make the slides, make the terms. Okay, affection and prediction of rainfall, okay, keywords to you, and you'll be able to find some good publications about it. Okay, it turns out that computationally it's not something difficult. Okay, computationally, essentially we are doing something like the differential, not really doing the differential equations, but doing something like extrapolation of some small cells of images to another cell, something like that. So, seems everything is fine, okay? Everything seems to be okay, but frankly, okay, I don't know how to solve the problem. Because, what's the real problem? The real problem is data integration. Data integration, I expect, would make you spend a lot of time in this hackathon exercise. And in terms of data integration, okay, we have temporal data integration, and we have spatial data integration. Okay, I'll talk about it a little bit in detail a little bit later. And of course, okay, you have to do the analysis yourself. And how many of you have taken AI course or machine learning course of some kind? Positive. Okay, so seems, well, at least you are smiling. Okay, thank you. Okay, at least you are smiling even if you are not raising hands. So I don't think really formal course taking is really necessary, and everyone is writing AI program of some kind nowadays. Okay, and the analysis will involve some kind of machine learning or artificial intelligence methods, which is expected, right? And among the myriad of possibilities of analysis methods, which one you choose, okay, is up to you. And you have to identify the problem clearly before you can do it well. So I said that one of the major problem is data integration, and there are two aspects of data integration problem. The first one is temporal, the second one is spatial. Temporal data integration, of course, is related to time. So look at this table, okay? This is essentially a summary of what has been told earlier this morning. Okay, we have reflectivity data, and the frequency is 6 minutes. And to me, the sampling accuracy is high. Essentially, if there is a piece of data for you, okay, you don't expect a lot of inaccuracies, there are a lot of problems in terms of quality of the data. Okay, I should say quality of data or something. Okay, and if you have gone through the few gigabytes of data that has been distributed to you today, you'll find that there is a rare case that we have missing data. So that's good. Okay. So essentially, we are saying that okay, Hong Kong observatories radar is working hard. Okay, it's working reliably, and well, as we can recall, okay, when would the unavailability of radar data something that we care about is when, for example, there is a strong typhoon, okay, super typhoon coming, okay. When the super typhoon came, sometimes, okay, there would be a few hours of downtime for the radar data. But the good thing is that Hong Kong Observatory is actually using 2 radars to cover the Hong Kong. Okay, we are only handling one of the data, one of the radar's data. Okay, and so operationally, okay, they can usually continue to spill out forecasts. Okay, even if there is a super typhoon. So this is good thing. Okay, 6 minutes. Radar photo. Radar photo, we have 5-minute frequency, and to me, the accuracy is kind of medium. Okay, it's not as accurate. Okay, I mean the data availability is not as high as that for the radar data. Okay, if you try to open a thumbnail view of all the images for a particular folder in the radar photo folder, you'll find that from time to time, they are missing radar photos, and if you look at the file names, you'll find that they may not be continuous. Okay, continuous in terms of 5 minutes every photo. Okay, sometimes it skips, and the time period between 2 photos is 10 minutes or even 15 minutes. Okay, spend a little bit of time familiarizing yourself with the data, and you will find that this is a problem. Okay, and we have traffic snapshot. Okay, we have high frequency photos, 2 minutes. Okay, 2 minutes each photo, but the sample accuracy is actually quite low. Okay, we can see quite a lot of missing photos, and if you look at the timestamp on the photo, okay, the timestamp is something that is overlaid, the text that is overlaid upon a background on the photo. You'll find that the timestamp on the photo and the timestamp in the file name may not always match. And that could be a problem. And that's why earlier in the morning, okay, it has been suggested, okay, if you really want to find the exact time of the photo, okay, you may have to recognize the need to text on the photo rather than trusting the file name itself. And in all cases, file names are indicative time of sampling. The reason is that even if I say that radar reflectivity data has high accuracy, okay, every 6 minutes there is really one piece of data coming, and it is accurate to the second. Okay, in practice, okay, it takes time to sample the data. Okay, for example, the radar. Well, how a radar works? Okay, it does a lot of sweeps. Okay, first it does a sweep like this. Okay, and then elevation comment higher and another sweep, and then elevation higher and another sweep, and how many sweeps are there? 4 or 5. Okay, another higher elevation and another sweep, and with all these four or five sweeps, okay, I forgot how many. Okay, with all these sweeps, which generate plane position indicators, okay, which generates cones of data, okay. The radar processor will integrate all these data and find out what the image should be if we are viewing the sky at 3 kilometers above sea level. Okay, and that's why we are dealing with 3 kilometer constant altitude plane position indicator stuff. Okay, so all these sweeps will take time, and essentially we are saying that the points are calculated by the radar processor, and we cannot assume that all the points appear at exactly the same time because we cannot really take a snapshot of the atmosphere. But this is something that we and every meteorological weather station, okay, meteorological center is using. So we just take it, and but if you really want to analyze to a accuracy or temporal accuracy of less than 5 minutes, then we have to bear that in mind. So practically, there's not too much of a problem actually. But then, the real problem is that we are dealing with data whose temporal frequency is different. So how can what kind of question can we ask? Okay, so for example, okay, if at minute 0 of an hour, all 3 pieces of data appears, then at the second minute, okay, traffic snapshot will update. 4th minute, traffic snapshot will update. In the 5th minute, the radar photo will update. 6th minute, the traffic snapshot and radar relativity will update. And it is difficult to find a point in which all 3 pieces of data are available. And so we have to do some kind of data wrangling so that we can ask the question, okay, well, I want to know how the weather, how the traffic is affected, okay, at 11 hours 35 minutes. Okay, I know that at 11 hours 35 minutes, okay, only weather photo appears, but not other things are not there, and I have to do something. Okay, so the question is, how can we do this? What do you suggest? Too simple a question, right? Interpolation, of course. Okay, so this is the standard answer. Okay, if at 0, if at time 0 the value is 5, and if at time 6 the value is 12, and so I'm asking what is the value at time 2, then I just do a linear interpolation, and I know that at time 2 the value is 4, something like that. Okay, so simple interpolation may work, but the question is, we are dealing with these 3 kinds of data: radar relativity, radar photo, and traffic snapshot. And how can we interpolate radar photos or radar relativity photos? How can we essentially, okay, given 2 snapshots of blobs of rain at time 0 and time 6 minutes, okay, how can I generate all the intermediate pictures to make an animation? This is a hugely difficult problem. So my suggestion is not to do that. But still, we need to interpolate. So my question is, okay, what are we going to interpolate? Are we going to interpolate the raw data, that is the radar relativity or the traffic snapshot, okay, or are we going to interpolate the analyzed information? And if it is in analyzed information, what kind of analyzed information are we going to take from the data? This is something important indeed. This may also reduce our work afterwards. Okay, this is essentially reprocessing, right? So we may be doing a lot of reprocessing just to reduce for example, reflectivity data into some indications or some numbers that indicate something that can be interpreted, or we can be analyzing traffic snapshot photos, and the result would be a number or a scale in which the congestion scale or something like that, so that it can be interpreted. Okay, but still the question is, okay, how can we analyze it? Okay, it is itself a problem by itself. Okay, the good thing is that you are going to work in groups. So if some of you, okay, would like to look at this problem, okay, this can become a separate model, and this separate module could be integrated into your analysis module a little bit later on. And we have to ask, okay, what kind of data are to be produced in the analysis? Are we going to find out the amount of rainfall at a particular location given the radar image, or are we going to handle the reflectivity image by itself? Okay, of course you can actually handle the reflectivity image by itself, because well, earlier in the first section, you heard that actually this is possible to do affection, and so a blob of water here going to a blob of water here, you get all the vector fields, and the vector field would tell, okay, at a particular location, okay, where the water come from a few minutes ago, okay, and this kind of stuff. And if it is possible, then actually you can try to interpret the reflectivity image itself. Okay, it's up to you. But this is certainly something that you have to consider, because you are dealing with gigabytes of data, and even if the processing is not slow, okay, I tell you, okay, I've done a lot of this kind of stuff. Okay, the processing is relatively fast, okay, because it is essentially some kind of simple image processing operations. Okay, but then still you have to consider what is the output. Or you can bail and say that, hey, I don't care. Okay, I don't care to interpolate. If I'm asking what is the state of the world at 11 hours 54 minutes, then I just look at the nearest sample. Okay, 11 hours 34 minutes is the point I want to know, and I find that 11 hours 35 minutes there is a radar photo, 11 hours 30 minutes there is a radar reflectivity photo, and 11 hours 34 minutes itself there is a traffic photo, and that's okay. Okay, so it is possible to take the nearest sample that way, and you are spared with all the analysis and all the interpretation, which may make your system a little bit slower or a little bit more troublesome, okay, to program, or a little bit more buggy. But if you really take this approach, beware, okay, because this system is supposed to be used in practice finally. Okay, so the question is, if I'm asking for the data at 11 hours 34 minutes, what kind of data is available? All the data before 11 hours 34 minutes will be available, but not anything afterwards. Now you have the full data set, of course. Okay, you can use future data, but in practice this is not really possible. So when you do a training, make sure that you are not using future data to predict the future. That would be a grave mistake. And tell you, okay, this is a mistake that is easy to make, because future data is just a difference in index usually in your array. Okay, so you are using moving window or something, and the index is off by 1, and you are using future data to predict the future. Okay, be very, very careful when you handle data that way. Is it okay up to this point? Okay. So, and another question is, okay, most probably you'll be using some kind of model that require training. Okay, and the question is can future data be used in training? Of course, okay. The answer is okay. Well, what kind of learning algorithm are you using? Are you predicting the future? And if you are predicting the future, you have to know the ground truth in the future, and the future data would be the one to produce the ground truth in a sense. Okay, and in this case, okay, it could be admissible, okay, to use future data to generate the ground truth for the prediction model. Okay, and but anyway, okay, there is a the philosophical discussion behind how and under what situation would this be valid, and so it's up to you to think about it. Okay, temporal integration, temporal data integration done. Okay, any question up to this point? Seems simple, right? Although hopefully you now feel the difficulty in practice, okay, when they are dealing with data. The other one is spatial data integration. Okay, so the same picture again, and the question is, what position does each pixel correspond to? Okay, we know about it. Okay, the center pixel, the image is 480 pixels times 480 pixels in size, and the center pixel is the location of the time motion radar station itself. Okay, very simple. Okay, so we know about it. But then, what if I move away a little bit? Actually, this has been covered in the modeling section as well. The image covers a radius of 256 kilometers, or about 256 kilometers. Okay, if you know how a radar works. Okay, and the projection is azimuthal equidistant projection. Okay, and I don't want to send you a reference paper in which well, more than 20 methods of map projections can be is shown. Okay, but anyway, okay, azimuthal equidistant projection, essentially you think about yourself as the radar, and you are pointing your finger in different directions. Okay, and if I'm pointing a finger in this direction, the distance matters, the azimuth matters, right? So essentially, radar data are theta R stuff, okay, and theta R stuff and with an elevation. So it's a cone is swept, okay. Cones of different locations of different widths are swept, and azimuthal equidistant projection essentially is a fancy way of telling you, okay, the distance itself matters. And why do I emphasize the distance matters? It's because the same amount of latitude difference or longitude difference could be different in different locations. Think about it, okay? At the equator, if you move east and north, okay, 1 kilometer, most probably the latitude change and longitude change will be the same. But if you are moving more to the north, move east 1 kilometer, the latitude change would, the longitude change would be more than when you move along the equator. Remember, okay, remember the globe. And if we move northwards, okay, it's the same, okay, in terms of the changes, okay. And so azimuthal equidistant projection does not preserve the difference in the latitude and longitude. And if you are interested, okay, go to this website. And yes, which apps? Yes. Okay, I hate Internet Explorer, but anyway. Okay, here it is. Okay. Okay, so this one, okay, is from MapWorld, and one of the map projections Okay, and it's neither equal area or more conformal, and you have all the latitude and longitude equations and so on, and you need all those tangents and sines and cosines to calculate exactly what latitude and longitude it is. Okay, and so okay, you have some more math to study. Okay, let's switch back to this one. 死啦，唔知用 window 添。Okay, okay, I'm back. Okay, and so spend a little bit of time. The good thing is that there are a lot of meteorological packages that handles this kind of conversion. Okay, so spend a little bit of time understanding the math behind, and then look for the right package to do the right conversion. And if you remember earlier, we have seen the equations, and the equations contains not only sines and cosines but also tangents. Do you like tangents? Do you like logs? If you have done any numerical computing, you hate tangents and logs, and arctangents and exponents as well. Okay, because it's difficult to be accurate, and a lot of times, okay, especially when the values are near zero or negative, okay, you don't know how to process that. Okay, so use the library if possible. Okay, if there is the library to do the conversion, okay, use the library and validate it if possible. Okay, of course you can follow the link here and use your own way to do the calculation between r theta and also latitude longitude. Okay, but beware. Okay, it is not as simple or as accurate as you may like. I've talked a little bit about what kind of data it is. Okay, so it is 3 kilometer constant altitude plane position indicator. And if you really want to know about it, okay, go to AMETSOC, okay, American Meteorological Society, okay, and it talks about CPPI, which refer to PPI, which are the conical sweeps, okay, and with the PPIs, that is the conical sweeps, together CPPI can be calculated, okay, it's the CAPI image. And going back to the data we have, okay, these are 3 kilometer CAPI data. So the radar itself is in some place, okay, pinned to a mountain or pinned to the ground, okay, pinned to somewhere, okay, and essentially, okay, what we are dealing with is something 3 kilometers above it, okay, and so we know we have to be very aware of the fact that we are not dealing with the same data directly below it, although you can use the 3 kilometer CAPI information to calculate latitude and longitude of each pixel or each point in the data, but it may not have a meaningful direct relationship between this point at the same latitude and longitude. Okay, because the Earth is a sphere, and so the same longitude and latitude, okay, 3 kilometers are farther than the same latitude and longitude on the ground. But that doesn't really matter too much, okay? Well, I shouldn't say that, okay? I say that a lot of times when we deal with this kind of data, we don't really care, and we assume that this is they are the same. Mainly because the extent of the radar is relatively small. We are talking about 256 kilometers only. Okay, and the curvature of the Earth actually already have played a little bit of into the picture, but then we very often still assume that okay, they are more or less the same as the corresponding latitude longitude points on the sea level. So we have the spatial problem already, okay, and we still have more spatial integration problem. This is the same picture I've shown you earlier. This is the Hong Kong image, okay, 2017, May 24th, in the morning, 10 o'clock, okay, 10:35, and well, what are we looking at? How can we use this to predict rainfall in the future and to predict traffic effect by radar in the future? How is it related to our problem? What do you think we can estimate by viewing the photos? Right? Foggy, okay, whether it's foggy, okay, whether there is something or raining or foggy or smoky, okay. So essentially he's saying that we can estimate the atmospheric condition or visibility, okay, by looking at these photos. And this is actually the case. Okay. And the next question is, okay, why does visibility matter? I don't know, okay, if I want to bluff, okay, I would say that, hey, maybe visibility is related to traffic accidents as well, okay. When the visibility is low, then there may be more traffic accidents, even if there is no rain. Very foggy days, okay, careless cars will bump into each other. It is a possible postulation, right? And so visibility is one of the things that we can estimate. And of course, if it is raining, okay, you may have the experience. Look out far, and you'll see that, hey, there's a rain cloud coming in or going from left to right, and you will be able to see the blob of rain, okay, far from us. Okay, and this is something possible. And so this is not something directly usable, okay, in a sense to help us to do the rainfall prediction, but it may be very helpful in predicting or in checking whether there may be traffic jams or traffic accidents. And we have the transport department's photo. Okay, well, we have hundreds of these. Okay, we look at the background. All these are the cameras, and the cameras really always look at the road, and so it's good. Okay, so look at this one, and if it is possible to find out which road it is, then it would be very useful. Okay, and to find out, okay, the amount of traffic jam there, or the amount of rain there as well. The good thing is that this is a reasonable postulation. The bad thing is that the resolution of these images are lower, okay, than the high definition camera used by Hong Kong Treasury. And this is essentially what you have. Okay, and essentially you have to guess, okay, this is a car, this is a car, this is a car, this is a car coming, this is a car going. Okay, so it seems still okay because they are red lights. Okay, and the Hong Kong law requires require the cars to use lights when it's dim and after sunset and before sunrise. Okay, so you may be able to infer something. But of course, there may be occlusions. Okay, for example, if there is a lot of cars, okay, and one car may be obscuring the lights of another car, and you may not be able to just count the number of red pixels to estimate the severity of traffic jam. And back to our question: where is the road? Which road it is? I don't know. Well, we have the metadata. Yeah, try to look at the metadata and try to pinpoint exactly which road it is on the map. That requires a lot of work, and that's why I say that, well, possibly a lot of reporting, a lot of data wrangling to help you to do the analysis is needed. Okay, before you are able to fit the whole set of data into some model for analysis. Okay. camera position. Okay, we have all these. Okay, very nice stuff. But exactly which row is it? I don't know. Okay, in the textual description there is description as well. Okay, tells you which row, but which section of the row we don't know. And so it goes back to our earlier question. Okay, can we use data from other sources? And the answer is that it is possible to use the data from the government portal. The government data portal contains a lot of stuff, okay, published by different departments. Transport department published some data about the road network, the center line of the roads, and things like that, okay, in the data portal. You can in the data portal you can filter the data by department, filter the data by time, if I remember correctly, or something like that, okay, or by name, and it is up to you to explore, okay. If you want to, for example, draw a picture, draw the row on the map, then these data would be useful, and these data are not something in our data set. Okay, so temporal integration, okay, interpolation, okay, or ignore it. Spatial data integration, how to do it? Well, the same answers, okay. We have this stuff, okay, and the answer is still interpolation. Can we? The question is, can we interpolate the data? Take the one in the bottom, okay. The picture in the bottom shows the weather photo stations, and if you have gone through the data, you'll find that the weather photos for this one, it looks at this in this direction. Okay, for this one, it looks at this direction. For this one, it looks at the sea, and this one looks at the sea as well. This one very far looks to the sea as well. This one, okay, is Hong Kong all, okay, looks to the east and looks to the west, and this one look at the sea, and so on. Can we really interpolate? Suppose we have a magical algorithm that tells, okay, the visibility at this point is 10 kilometers, and visibility at this point is 5 kilometers. Can we draw a line and estimate that, okay, in the middle, okay, it is 7.5 kilometers of visibility? Or does it make sense? Okay, be very careful, okay? And also, okay, unlike radar data, okay, cameras are not kilometers above ground. They are fixed to some building, some structure, or the ground level, okay? And so the cameras may be different in altitude. And considering the 3D environment and also the direction they look at, okay, interpolating the values in from the weather photos, okay, may not be always a good idea. In some cases, it may be, okay, but it may not always be a good idea. Because cameras are not kilometers above ground, hills and cushions and different altitudes, simple interpolation may not always work. Okay, that's our conclusion anyway. And also the direction of weather photos matter. And I spent a little bit of time looking at the description and trying to draw little lines. Okay, we call it antenna lines. Okay, from each weather photo station, and so you'll be able to have an idea. Okay, why many of these cameras look at the sea or look at some place very far away. Okay. The reason is that, for example, if I want to see whether we'll be able to whether the visibility is greater than 20 kilometers, this station turned out to be a good one. This station, okay, look at the south of Hong Kong and extend the map a little bit at around the location of my mouse. Okay, around the location of my mouse over here. Okay, I scroll it up a little bit. Okay, so I'm talking about this station. Okay, imagine the map is large and around the location of my mouse there is a there are a number of islands. Okay, 淡江列島，我哋貪乾呢度就係 okay, and these are the islands which are 26 kilometers from this point, and very nice way to say whether the distance, okay, the visibility is greater than 26 or less than 26. Something like that. Forgive me if it is not 36, okay? Find the exact value for me if you have the idea. Or of course, okay, we can ignore the problem. Do not care about interpolation, okay? For the transport department pictures, okay, they look at the streets, they look at the roads anyway, and so I just care about the data for that part, okay, and that's all. And so, in conclusion, okay, just because of data integration in terms of spatial and temporal dimensions, you have a lot of data preprocessing to do. And I suggest you to try to get familiar with your data early as possible. Okay, after today, you have a few gigabytes of data already, and so I guess, okay, doing that early would be useful. Okay, I don't think it would be good to keep you listening, and so let's take a break, right? Okay, it's already 1 hour, and let's take a break, and then I'll go on talking and switch to the workshop itself. Okay, so anything to say?
Okay, so thanks, Dr. And before the break, I would like to make a correction. Okay, I've made a mistake in my previous slide on the logistic. Okay, so now I will update it and then post it in our homepage. Okay, basically the date is 12 to 17. So the starting open ceremony will be on October 12th in Hong Kong Observatory. And then the closing ceremony will be October 17th, okay, which is on CHK. But as I mentioned, you are not required to start working on October 12th. You can work earlier. Okay, so once you have the data, basically everyone can start looking at the data, try to do the data cleansing and whatever. Okay, now the important message is here, forget about this two. Okay, the period is 12 to 17. The first day, opening ceremony, last day, closing ceremony. Okay, I'm sorry about that, okay? But anyway, hopefully I will not confuse you too much. Okay, now let's take a break and then I'll give it back to Dr. Yi. Okay, so maybe 10 minutes break, okay? And then we'll continue. So the closing is 7 years. Yes.
Wow. Okay, I'm back. So data integration, and since most of you have taken some kind of AI course or something, okay, I'll just very quickly go through what you may need to do, okay, and show you a big picture. Like every kind of data analysis, data analytic exercise, okay, what you need to do at the very beginning is to collect the data and then prepare the data for analysis, and then we do the actual knowledge discovery or data mining or intelligent process, okay, and then we verify the results or interpret the results and evaluate the process, okay. This is what the textbook tells us to do, okay, not anything interesting. So data collection for our exercise here, it is easy because we are kind of provided with gigabytes of data. But as you may know, okay, if you, for example, if you want to plot a map, okay, or you draw a map or plot the location of the roads, then you have to get some extra data from somewhere else, okay, and this is something that you may need to consider. And anyway, you get tens of gigabytes of data, and you need more data than that. And you have to also think about how you are going to present the results, okay? I'm still in the clouds, okay, what the final products or what the final deliverables would be. Okay, if you remember what has been covered in the modeling section, you'll find that, okay, it would be some kind of web-based report or web-based warning or web-based stuff, okay, to tell us to gauge the traffic, okay, to tell us about the traffic effect because of the weather, and also to do a little bit of weather forecast, essentially, or rainfall forecast, something like that. Okay, I'm still in the clouds. And well, actually, this is a good thing because, well, just read the specification again, okay? Read the notes in the morning again, and you have a lot of room to decide on how your interface would be like, and so on. And you may go as complex as having a 3D model of the Hong Kong, and then show which road could be problematic, okay, could be congested, or it can be as simple as some kind of text message or something, okay, that tells well, at your location there would be heavy rain or something. And visualization is one of the things that you may need to do. And most of the times when we talk about visualization, we think about scientific visualization like plotting graphs, plotting charts, and things like that. And if you think about plotting maps, you'll find that most of us do not know how to plot a map of Hong Kong, or where to get the data to plot the map of Hong Kong. Okay, later I'll show you some packages and some environments in which this is relatively easy. Okay, but then this is a completely new language, completely new environment for most of us. And of course, okay, dashboards, okay, if when you visit the page, okay, there's a dashboard kind of summary of all the analysis results of your website or of your system, then it will be good, okay. But well, anyway, okay, whether this is fat or useful is up to you. And of course, map could be useful. And data preparation, okay, after you collect the data, you prepare the data, and it involves processing and cleaning, as you have seen already. And we should remove noises, okay. And if you remember the talk this morning, okay, one of the radar images is shown, and some of the speckles have been circled and saying that, okay, these speckles may be caused by reflections from houses or the sea and things like that. Okay, and so this has to be removed. And there may be missing values for some of our data. Okay, should we fill in the missing values, or should we somehow handle them in a special way? For example, if there is a missing picture, how can we handle it? And even worse, if there is a picture, there is only half available. Okay, the other half is not available. I've seen these kind of pictures indeed from the data. Okay, I'm not talking about your set. Okay, but it's possible for the picture to be incomplete. How to handle it? Okay, something like that. And we should normalize the data as well. A lot of times, okay, essentially the same among the same data from different sources should be represented the same way. So either everything should be represented as reflectivity value, the Z value, or we apply the Z equals AR to the power B formula and find out what is the rainfall in millimeters per hour. Temporal and spatial integration is something that we need to do, and feature extraction is also something that we need to do. And this is the first time I use the traditional word of feature extraction in this section. The reason is that, well, essentially when we are analyzing stuff from a piece of data, we are transforming the data to something more succinct, okay, smaller or more a summary of the data that we are given. So, for example, given radar relativity, find the amount of rainfall at Hong Kong U. Okay, maybe I just need to look at only 3 or 4 of the pixels in the radar. Okay, and I'll be able to interpolate. Okay, but this can be seen as a succinct representation of the radar data if I care about the rainfall in Hong Kong U or the traffic condition around Hong Kong U only. Okay. So essentially, this is data transformation process. So different data mining books or data analytic books will use different names for that. And one thing to notice is that when since you are processing photos, the effect of sun, rain, and glass reflections and smog matters. Okay, it would be very interesting to go through one sequence of image. Just take any of the weather photos. Okay, start from the first one, mostly black. Okay, because it's midnight, and next. Okay, mostly black, and then you see sunrise, and then everything become bright, and then everything become too bright because the sun shines directly to the camera, and then later, okay, it's become better and so on. The question is, how can you normalize it, or how can you handle the effect of the sun? And if you are serious about it, okay, there is more math to play with, because, well, actually, there is a formula for you to calculate the position of sun given latitude, longitude, and day and time, right? And you'll be able to do this, okay, with relative ease if you find the right library, okay? And well, with the position of sun, it is possible to offset, or you'll be able to equalize the image a little bit. But then it's not only the sun, it's also the radar. Okay, we are looking at radar. So even if the sun is supposed to be shining directly above us, but if it is bad weather, raining, then you still see no sunlight. And so you have to consider this kind of thing. Pretty difficult task by itself. And after all the pre-processing and cleaning and so on, okay, what's next is to feed your data into some kind of intelligent process. And the intelligent process very often involves training of some kind. And the idea is to use existing data to train a model. A model is a representation of the knowledge that you are going to use. And then make sure that you don't use all data for training. You set aside some percentage of data for testing. For example, okay, 70% for training, 20% for testing, or 30% for testing. And the idea is to design a criteria, to evaluate how good a model is. Okay, because you are essentially training a model. Okay, certainly this is the most boring part of my talk here, because this is very high level. Okay, it's not very different from your data mining course or AI course, and does not seem to be directly related to our work. So I'll tend to go fast. So the data set for training should be different from that for testing. The reason is that we don't want the model to overfit. If we use the same set of data for testing and training, there is a high chance that the model will overfit the data used to evaluate itself. Of course, there's the name for this kind of testing. Okay, it's still admissible, but but usually we try to avoid it. Okay. And we have to set aside a little bit of data for validating the model itself as well. For example, to see how well the model performs in face of real data or unseen data, and make sure the model works for the general case. So a lot of times, okay, in the training and testing part, we are dealing with a lot of models and try to select the better one. And in the model validation stage, okay, we try to see whether the better one is really better, okay? And by talking about a lot of model, it could be the same model or the same algorithm with different parameters as input, okay? And for example, if you preprocess the data by doing a Laplace operator on the image, okay, you take out all the edges, okay, and but still, okay, you can use a 5 by 5 Laplace, and the result could be different, something like that, okay. It could be anything parameterized. You consider it as different models, and at the end, okay, you have to refine the model itself. And afterwards, okay, you try to verify the result, apply the model on new data, and analyze. The analyst tries to see if the result is meaningful, which means that you have to be reading the output as well and trying to interpret the output as well. For example, your model says that, okay, it's going to rain, and what you need to do is to look at the case, so see whether it is really going to rain. Okay, look at the photos and look at the weather data. Use your brain to interpret to see whether the intelligent program is really intelligent, or is just luck, or is drawing conclusion from the wrong path. This requires a lot of experience indeed. Okay, so this is why data analysts are so expensive, okay, to hire. And often it involves visualization of results. Okay, go to Google Earth and you'll find that there is a picture. Okay, like this. Okay, so the green ones are the roads that are good, and the red ones are congested. Okay, and these are the blocked ones, and this was taken at about 3 o'clock this morning, and I don't know why so many blocked areas. Okay, I haven't been reading news. Okay, near Central. So evaluation process is to continuously refine the model and to choose the right models and parameters and training, testing, and validation data, and the criteria for evaluation as well. So what I want you to do is, okay, or what you should be doing is to explore the data. Okay, explore the data is very important as a data analyst, because you have to be familiar with the data, and you are practicing the art of looking at your data, rapidly generating hypotheses. Okay, look at data, and why are there so many pictures, okay, they're exceedingly bright, okay, and I may generate hypothesis, okay, maybe the sun is in the wrong place, and I calculate the sun location and see whether it is the situation something like this. Quickly testing them and then repeating again and again and again. So human plays a major role in the artificial intelligence indeed. This is why we hear stories like a human listening to the utterances, okay, to the Amazon gadget, okay, and things like that, okay, which people hate. And the visualization is also important, okay. I don't know whether some of you like to use visualization packages, okay, from d3.js to Matplotlib or something like that, okay, but if you like visualization, okay, you'll be able to find a lot of new stuff, okay, by participating in this hackathon. The analysts will get more and more familiar with the data in the process, and I hope that, okay, sooner or later you will be able to tell me something interesting about the data that you have in hand. Okay. So I guess there is a part that is mandatory. That is well, because I have to talk about fundamentals, so AI textbook. Oh, well, which book do you use for the AI course? No book. Okay, no book is not used anymore. Good. Wow. Good. Okay. So what is artificial intelligence? Okay, philosophy. Okay, this is the part I like most when I teach AI courses. Okay, and artificial intelligence is to build computing systems that thinks like human, thinks rationally, acts like human, or act rationally. So four combinations. Okay, and these are the four philosophies of artificial intelligence since 1960s. And I guess if you have taken AI courses, okay, we have the weak AI claim that computers can be programmed to act intelligently. So the only purpose is to fool the human being, okay, that the program looks intelligent. Okay, so the Turing test would be able to tell whether a computer or a program meets the AI claim that is weak. But there is also strong AI claim that is more philosophical. That is, a computer has a mind and can think. And this points us to mind body problem of dualism and materialism, and bring us to the refutation of the strong AI argument using the Chinese room argument. Okay, this is one of the 2 pages of AI course summary that I think is important. Okay, I know a lot of professors teaching AI do not agree with me, but I think this philosophy part is actually the most important part of artificial intelligence to me. Anyway, the second page. Well, if you follow the book that is used by most universities, okay, the AIMA book, the Artificial Intelligence Model Approach book, it goes on to talk about agents, okay, different kinds of agents that does different things. Simple reflex agents just look at input and spew out output, and model-based reflex agents, okay, try to remember something, okay, so I try to build a model and output using the output of a model and so on. And these are the possibilities. And then, okay, machine learning would usually be quite late in all those AI books, and they are categorized as supervised learning. Okay, essentially you study given the answer. Okay, and so I tell you this is black, this is black, this is black, and later I'll ask you, okay, what is this color? And you say that it's not that, and that's something like this. Okay, every time you study, every time you learn, you have the answers at hand. Unsupervised learning, infer without answers given. Okay, this comes with that. Okay, this comes with this, and this comes with that. Okay, something like that, and you don't know what they are talking about. Okay, there's no definite answer, but if you see enough examples, you'll be able to put things together. Okay, put similar things together, put things that should be together, and so on. And that's reinforcement learning. Okay, some people would put it in as a category, but some not. And the answer is not given explicitly, but then every time the agent does something, it would incur some gain or loss. So every time you do something, okay, this would be a gain, okay, a reward or a punishment. Okay, so all enough, right? And so some models. Some models, okay, I think these are things that you may have already known. Okay, decision trees, rules, regression, base decision. Okay, so it's essential probabilistic stuff. Hidden Markov model. Okay, what the next state is about. Clustering, like putting things that are similar together. Most probably, it would be a unsupervised learning outcome. Support vector machine is something very hot in recent years. And genetic algorithm-based models are hot, a longer time ago. Okay, and artificial neural networks become something of a hot topic in recent years because nowadays we have enough hardware power and software power to be able to build neural network models that are efficient enough. So we have backprop, okay, and the new kid on the block is long short-term memory. Okay, for some reason, this architecture of neural network, okay, this is actually a kind of recurrent neural network. Okay, this architecture suddenly becomes very, very hot in many areas, from weather prediction to to finance prediction and the behavior prediction and things like that. Okay, and hierarchical learning has been there for more than 30 years indeed. Okay, and hierarchical learning has been there. Okay, new level layers of neurons connected to each other. Okay, to learn higher level concepts. And now with the new word or new name of deep learning, things become very, very, very hot. Okay, but anyway, okay, there are a lot of fat in the artificial intelligence. Anyway, okay. Okay, boring stuff done. Okay, I see that some of you are starting to fall asleep, and so I spent a little bit of time to tell you something more practical. And as I have kind of told you very early, is that I'm not able to teach you how to do because I don't know what your final outcome would be and what you would like to analyze. So I'll introduce some language platforms and also software packages and environments for you. I know that a lot of you think about AI as neural network or deep learning or something, but there is much, much more than that. Of course, okay, everyone nowadays goes to Python, okay, and how many of you do not know Python? Well, my first Python book is a Python 1.1 physical book this thick. Okay, I put it into my bookshelf. Okay, read only 1/5 of it. Okay, and find it not interesting, and I didn't start really writing Python until in recent years. And well, I still wonder, okay, why it becomes so hot for everything. Okay, the other language that is so hot for everything is JavaScript. JavaScript now rules the world. Okay, from the front end to the back end to the analytic engine. Okay, everything is done in JavaScript, which is a very dirty language. I don't know whether you think it is the case. Okay, but I think it's a very, very dirty language. Okay, sorry. Okay, and but Python is a little bit less dirty, but so go to dos.python.org or www.python.org, and if you don't know the language, spend a little bit of time. Okay, it's not difficult to learn, but it's the packages that are difficult to learn. Okay, there are too many packages, and you have to choose the right ones. But talking about data analytics, there's another language that has been there for a long time, and this is the language called R. Okay, R is in a project called R project, and the project is for building an environment for statistical computing and graphics, and it has been there for decades already, 1 decade, I guess. Okay, something like that. And go to this website, and the reason I put R into the list is that many of the earlier machine learning model or data mining models have packages with R bindings. Okay, so it's something that is worth looking at. And if you like to have a graphical environment, then R comes with Rectal. Okay, Rectal is a graphical environment for R. And of course, Python, we have a lot of possibilities, which include something that we are going to introduce next time in the coming few pages. Okay, but we are dealing with meteorological data. And meteorological data, if you are old enough to deal with meteorological data, most probably you may have written programs in NCL. NCL stands for N-Car Command Language. It's an integrated language for scientific and data analysis and visualization, and plotting things like maps of the world and overlaying the radar data on the map. Okay, semi-transparently and things like that. Okay, generated animations is something that is pretty easy. Okay, for NCL. Okay, and this is something that is worth looking into. This one is a kind of itself. Okay, if you like Java, if you love Java, then you have to use Weka. Okay, I guess some of you have already tried it. Okay, it's the easy package for data mining, for data analysis, and Weka is the name of the bird. This bird. Okay, and this bird is indigenous in New Zealand. Okay, and Waikato University is in New Zealand, of course. And in the environments, okay, if you decide to go to the Python way, then the Anaconda distribution is the data science and machine learning platform for Python and R. Okay, the idea is that this Anaconda distribution contains packages for Python and also supports many languages. Okay, not only Python and R, but also things like Scala, Julia, and things like that. Okay, so how many of you write in Scala? Julia. Okay, come on, try them. Okay, hope you are not called Julia. Okay, so try them. Okay, Julia and Scala, SCALA and GULIA. Okay, for different purposes, and they gain a little bit of traction for some specific purposes. And if you want to have an interactive environment for Python and R and Julia and Scala, then you can use a Jupyter Lab. Okay, go to jupyter.org and install the first package under Jupyter Lab, and you have an environment that is web-based, and you'll be able to write Python or programs in other languages. Okay. Interactively and be able to save them and share with your friends. So the actual packages that could be useful is, of course, OpenCV. Okay, I guess many of you have the experience of using OpenCV. And if you think of the radar images as real images, then the OpenCV, of course, is the package to use. And there's Python module or Python binding for OpenCV as well. And if you really like to go the Python way, then the package to use is SciPy. SciPy is actually an ecosystem containing a number of libraries, okay, for different purposes. For example, plotting graphs, okay, and scientific library, scientific computing library, dealing with vectors and things, numbers, okay, n-dimensional arrays, sparse arrays, and things like that. Okay, interactive Python and symbolic mathematics, okay, and also data structure and analysis and so on. And there is a hidden little package called MatPy. Mat stands for meteorology. Okay, so this is a package for meteorological computing written in Python. So the line is Python tools for reading, visualizing, and performing calculations with weather data. The good thing is that if you have the chance to deal with real weather data, you'll find that getting the data from the data source, okay, is itself a troublesome problem. Okay, it's itself a difficult problem because, well, the data is in so many different formats, and HDF5, HDF4, okay, and every radar has its own format and so on. And so the good thing about MatPy and NCR earlier, okay, NCL earlier, okay, integrate all these in a good way. To do machine learning, okay, scikit-learn is the basic package to under Python for that. And this is the new kid on the block. I have no experience with it, okay, but in my preparation, okay, I find that there is something called H2O open source platform. Okay, supposed to be a scalable learning API for our Python, Scala on Hadoop and Yarn, and also Spark. Okay, so when you need to use Hadoop and Yarn and Spark, essentially you are doing distributed or parallel distributed computing. Okay, using multiple nodes to do a calculation for you, and this seems to be built specially for it. Okay, there's a package called Sparkle as well. Okay, H2O and Sparkle, two different packages. Okay, H2O do the core thing, Sparkle do the communication stuff. Okay, but I confess I don't have experience on this. Okay, and so if you use it, okay, you're welcome to share your experience with me or actually teach me how it could be useful. And everyone goes to neural network. Everyone uses TensorFlow. and everyone is happy trying the tutorials. And whether it is suitable for your own applications, I don't know. So check it out yourself. We're dealing with images, okay, either photos or radar images. And image magic is a tool set for image manipulation. It's nearly installed in every Linux environment. Okay, the reason is that you will be able to do image manipulation completely in command line, in using command line interface, and so this is something good. This is considered to be something good. Okay, and again, okay, I've been using it for years, but I confess I do not really remember how to use, for example, the convert command to a fluence level that I'm satisfied with. Okay, there are a number of commands, okay, like convert, that allow one format of image to be converted to another. Okay, but then how to use it? There are so many options that I will not be able to remember. So this is something that probably, okay, every one of us has to learn for a long time. And if you like neural computing, okay, there is Intel Neural Compute Stick, and this is the hardware, okay, a piece of hardware that plugged into the USB port of your computer, and there are chips, hardware chips, okay, that you can download the program to run, okay, a neural network over there. And of course, okay, normally we use CPU-based computing, okay, and because I mentioned neural compute stick, I have to mention this, okay, for the sake of, well, not really completeness, but at least this has to be mentioned. So reference, okay, this is so-called my AI book that I followed, okay, 2-page summarize this one, okay. If you really use this book, then it is something 10 years ago. But this year, in December, the 4th edition will be out, and it's not December yet, so maybe someone is still waiting. Okay, aima.cs Berkeley edu. And OWL and Rectal, okay, this one I find that is available in most university libraries. And this one is the book for WeatherHack, and I think it's quite useful. I like this book quite because it doesn't make things difficult. Okay, it's easy to read the content of this book. And newer stuff, okay, Essentials of Data Science, okay, discovered using OWL, and again by Graham Williams, which is the author of the book here. Okay, Rectal and OWL. Okay, Graham Williams seems to like to use OWL, and another one OWL for data science. Okay, so I try to push OWL up a little bit. Okay, so before you decide on a particular method, okay, try to see what all those packages and all those alternate languages, especially if you haven't tried it, okay, can offer before you decide on an environment. I understand that a lot of students try to decide on an environment or decide on a method of doing things because they know this. Okay, I have been writing C# for so many years, so it must be C#. So I try to find whether there is some C# package for machine learning, and finally, of course, you can find some. Okay, and the C# guy will never jump out of his C# environment. Okay, try not to be confined by the language you know. Okay, try to look from the problem's point of view. Okay, from what you need to solve. Okay, and select the right thing. And of course, okay, A.M. Turing's classic paper on the philosophy of AI, and in case you don't know what Chinese room argument is, okay, go to platostanford.edu, okay, to read about it. Okay, so much for me. Okay, any questions for the lecture part? Okay, so we have an hour, a little bit more, so it's good. Okay, and the next one is the VM1. Okay, So for those who have who do not have the who cannot run the VM, is it that most of you have downloaded the VM? And is there anyone who cannot run it? Yes, no, no. Okay, suppose it's like this. Okay, go to F drive, hackathon, and right click. But if you cannot run, most probably because the extension has not been installed. And go to F drive hackathon and go to this window, right click and command prompt admin. Okay, command prompt admin, here you have this. Choose administrator. This is a very secure administrator because there is no password. Okay, yes, and then you have a restricted administrator over there. And see if you can go to F drive. If you cannot go to F drive like me, then go back to desktop. Oh no. Windows desktop. Okay, and so no. So copy this Oracle extension to a desktop. Okay. And CD to a desktop. CD to a desktop. Desktop on bin. So it's Windows desktop or users desktop or something. 我邊個呢嚿嘢 So I go to the desktop. This PC desktop. So it's like this. Okay, and this PC, okay. I move it here, okay, videos. Okay, whatever, okay, move it to somewhere that you can access. Why? 救命啊! So I don't know where it is. The idea is to move it to a place that you will be able to run that in command line under the administrator environment. And that's it. Okay, so command prompt admin, administrator, yes, and what am I dealing with this? Okay, Windows System 32. Okay. I directly put it into Windows System 32. Okay, Windows System 32. Not here. C drive. Windows System 32. I better be lazy. Okay, I get one. And this one is my videos, and I put the whole thing in. Okay, continue. Okay, administrator, yes. I just be very lazy. Okay, and I'll be able to see Oracle VM VirtualBox. Okay, Oracle VM VirtualBox something extension pack, and I just enter, and this will run. We install. Scroll down. I agree, and it's done. Sooner or later, okay, it's done, and fail to install. Access denied. So I'm already using the command prompt of super user. Okay, maybe my computer is different. Okay, I've seen some of you. Okay, successful, and so this is done. I assume that this is done, and what's next is to go to the WeatherHack folder that you have copied from F drive and double click on the VirtualBox, and this one will be running. Okay, you may see that this is too large in size, and in this case, okay, I'll go to the settings and display, and the scale factor is 100%, and hopefully it will not be too large, and the password would be 20 minus WX minus 19. Okay, 20 dash WX dash 19. So you just copy anywhere that you are able to access using your command prompt. So for the VM part, okay. Now who's not there yet? Okay, I'll walk around and make sure that all of you can do it first. So this is the password 20-WX. Anyone still have problem? Okay. Give me for this funny sizes. Anyway. Okay, so this for those who have started the virtual machine. Okay, notice that there is a WeatherHack folder at your home, under your home. Okay, so just cd there, and you see there is a section, a folder called code. So essentially, I'm at home WeatherHack code. Okay, and when you list, you see the radar image and radar mask. Okay. Radar image itself, okay, is a PNG file, so you'll be able to see it using tools like XV or a browser. Okay, so I'm always lazy and just this way. Okay, and I see the image. Okay, so it seems okay, and I'll just say background. And the question is, okay, how can we process the mask? Okay, look at this. Okay, we have the PNG, which is the radar. We have the mask file, which is 18 kilobytes only. Okay, and well, I said that the image itself, okay, the radar.png itself is 480 times 480 in terms of pixel count. Okay, so I can identify radar.png and it will tell me that it is 480 times 480 PNG. Okay, and this is 8-bit sRGB, okay, 256 color, so essentially grayscale. Okay, and the size is so much, okay, and so on. Has anyone used identify command? Most of us using Linux, okay, have this in our installation because this is one of the image magic commands. Okay, identify is just to tell you what is the format of the file. Okay, if you know that it is a image file of some kind. Should I turn off the light? Okay, so better that way. Okay, so identify the file and that will be done. But then what is the type of a file for this radar.mask? Okay, when you don't know what type of file it is, okay, what can you do? Okay, large enough, right? How can you find out the type of file for this radar.mask? Well, seems you are not very familiar with Unix, right? File and radar.png, and it will tell you that it's a PNG file. File radar.mask, and it will tell you that this is a Z library compressed data. Okay, the mask file itself is Z library compressed data, and so the question is, okay, how to decompress the Z library compressed data? Well, good guess would be Z library or something, okay, Z lib or something, and there is a Z library flag or something. Okay, so it seems okay, and I'll just enter and Z library flag uncompress or compress. Okay, so uncompress, so seems fine. Okay, so radar.mask, and I don't know where the output would be. Okay, to be safe, not to mess up my terminal. Okay, I make it radar.uncompressed. This is my guess. Okay, I don't know how to use set live frame indeed. Okay, but of course, okay, my guess is wrong. Okay, I think I make it smaller. Okay, so that you can see better. I hate the auto sizing. Okay, do it all over again. Okay, what I know is, okay, radar.mask is this library compressed data, and I just try set live phrase, and I get uncompressed or compressed. And so what I did is to guess. Okay, it must be used like this. Okay, uncompressed, and then the input, and then the output file. Okay, and I'm greeted with an error message again. Okay, so of course, okay, we have to read the main page. Okay, set live state, and it's a raw set library compression program, and so on and so on. That's all. Okay, so the whole thing is compressed or uncompressed. So it means that it is not supposed to be followed by a file name. So because this is Unix of some kind, this is Linux, so I gather it is designed to be a filter, right? If it is designed to be a filter, what should we do? Okay, send the file cat radar.mask to that set live phrase uncompressed. Because it's a filter, the output has to be redirected to another file. Okay, radar uncompressed, radar mask, radar 叫咩名好啊？ What name should I use? Okay, uncompressed. Okay, and it's done. and I really have a radar uncompressed file. Okay. Do you think I've done the right thing? Of course, I don't know, but we can make an educated guess. Okay, the educated guess is that, well, after uncompression, okay, how many pixels should there be? It's 480 times 480 pixels, right? And the number of pixels is 230,400. And it is exactly the size of this file. So I have reasonable confidence that I have done the right thing. Indeed, this is the case. Okay, this is how we handle the files in the mask directory. Okay, and so we have this file and we have this raw file. Okay, so the next question is how can we make it a mask, or how can we visualize the mask? Becoming difficult, right? How can we visualize the mask? How to convert raw data into some kind of PNG file or whatever? Well, start writing program now. Okay. Anyone who have tried Python before? Positive. No? Okay, so let's try now. Okay. JUYP TER-lab. Yeah. JUPYTER-lab, sorry. Go Jupyter Lab, and a server will be running, and your browser will be fired up, and you got two environments for Python 3. One is for notebook, one is for console. The notebook is an interactive environment in which you will be able to type in Python programs, okay, or Python statements and execute it, okay, line by line. Okay, so it seems to be better for experimentation than using a text editor and edit the whole program and just run it every time you change something. Okay, so a lot of people who use Python use this way of testing things. So I click on this one, and so the question becomes: now we are at that folder. Okay, Control Z background. And we are at this folder, we have a radar.png, we have a radar uncompressed. Okay, how can we visualize the radar.uncompressed? And so I have to somehow, okay, use Python to read. Well, let's try the radar.png first, right? So I have to somehow try to write a program to let Python read the content of the PNG itself. Okay, anyone know how to? Well, not knowing is normal, indeed. Okay, and but among all the packages that I have introduced earlier, which one do you think could be useful for manipulating images under Python? OpenCV, okay, OpenCV2, okay. OpenCV, and it is one of the packages that has already been installed in this VM. Okay, that's why I distribute VM. Okay, otherwise we'll be installing this and that and that. Okay, and OpenCV and OpenCV by itself. Okay, it is a environment that is written in C. And so the binding is normally in C, and so if we want the resources, then we'll be looking at the API for for the package in C language. Okay, and but what I can say is that with OpenCV, the easy way to read the image is use the function imRead. Im is image. Okay, image read this one, and this is the API. Okay, image read, and then this is the file name, and then a flag, and that's it. Okay. So the question is, I'm writing Python now, so how can I use OpenCV? And the answer is that I go to import a package called CV2, okay, which is the OpenCV Python binding. Type this and then press Control Enter. When you press Control Enter over here, this part would momentarily change to a star, which means that it's running. And after it's done, it becomes a number, which shows you the result. Okay, and the result is nothing, and so nothing is output. You can click on this plus sign, and after import this import CV2, what I can do is to read the image. And according to the API documentation earlier here, okay, is the CV package imRead, and then the string of a file name, and then the flags. And since the flags matter, and so the flags itself read a little bit more API, and flags that can make values, okay, and one of the most, and click on this one, you see that there is the imRead of grayscale, okay. And so what I can do is CV2 imRead. What's the name of a file? Radar.png and cv2.im radar. What scale? What grayscale? imRead underscore grayscale. Okay, imRead grayscale. Okay. Control Enter. Control Enter. Control Enter under a box makes it run immediately. Okay, if you Control Enter, and this will become a number. A number tells which statement. This is the first statement to have run in this environment. Okay, you have run it multiple times. That's okay. Okay, so just Control Enter once, and this import CV tool has been done. And the next one, okay, Control Enter once, and this reading, okay, would result in an array. And I find that, hey, I forgot to store the array in some variable. So I go back and say IM is assigned to the result of this one, and Control Enter as well. And the third one result does not return me anything. It's okay up to this point. So there's no problem for this one. Then the question is, okay, how can we open the mask and generate a file, generate a Python file? So well, how many of you have written Python before? Positive. Have, okay. Okay, so a difficult question, how to read a raw file in binary. It's really not easy. Okay, so open. Okay, open is a built-in function. Okay, and the file would be radar dot. What did I call it? Uncompressed. Yeah, radar dot uncompressed. And I have to make sure that it is in binary mode. So it's read only and binary. Okay, so this one will give you a file handle. Okay, so this file handle is stored in the variable f. Control Enter, and f would be a file handle that I can try to use. And f.read and one line you will be able to read the whole contents of the file. Enter, and to get all these binaries. Okay, this is not good. Okay, I don't like this. Okay, because I'm reading a binary string and it's dumping me the contents of that binary string, right? And so I want it to become an array, because an array is the way this image is represented. Okay, an image in CV2 or OpenCV under Python binding is represented as a NumPy array. Okay, and so I want to convert it into array. And so the question is, how can I do this? Okay, so binary B become this. Okay, I just read, and there's no output. And so binary and array version. Okay, I call it BA. And for those who knows how to write Python, okay, I use a facility called array. 死唔記得個叫咩添？ Okay, I use this facility that is okay. M for so for every value in B. Okay, so array. Yeah, so this one okay is to generate array, and every element of the array is an element in B. B is the binary string that we have just read. So every element becomes a value in the resultant array. Okay, so after this, what I get would be a very long array of numbers rather than long array of binary values. I want to verify, and so BA enter, and it's nothing. Okay, so B is not there yet. Okay, I'm not sure whether I've read the right thing. So let's try B. Okay, B is nothing. Okay, so I have to go back. Okay, to make sure that B is something. Okay, so F is open and F is red, and I go back to see what is B. Okay, B is here. Oh, it's good, and so BA is V for V in B. Enter. Okay, so it's not good. So BA enter. Okay, so we get an array of numbers. So, well, what you have seen is that I'm debugging, okay, under the interactive environment. Okay, I don't know what I've done wrong. But then the good thing about this Jupyter environment is that I'll be able to run statements one by one, okay, interactively, and it will tell me which statement, okay, I have run last time, so I know that I've done this and I've done this and then this and that, okay, and if I'm satisfied with this one, then the next thing I can do is to resize this array to a 480 times 480 array. Is it okay? So how to resize it, and it comes to a little bit of insider information about how CV2, okay, or how OpenCV represents images. OpenCV represents images using NumPy arrays, and NumPy arrays are essentially arrays of arrays. And so the first thing you have to do is to make this BA, which is the normal array or a Python array, into a NumPy array. NumPy itself is a package, and so I have to import the package. Okay, so the standard way to do it is import NumPy. NumPy is long, okay, so as empty. And Control Enter, and the NumPy package has been taken in. And so it's B's NumPy array, okay, so BNA becomes np dot array of BA. So this is to convert the normal array of Python into a NumPy array of the package. Okay. Okay. So if I use I try to look at what BNA is, it is an array of something, and this array corresponds to the fact that it is of type NumPy array rather than a normal array. Is it okay up to this point? Okay, so we have a NumPy array, and the good thing about the NumPy package is that now we have an array that is 404 times 400 in size. Okay, one-dimensional array, 200 and 200 and something thousand. Okay, in length. I want to resize it into a 480 times 480 array, and the good thing is that NumPy package has a resize function, and BNA resized. Okay, sorry for the bad names. Okay, but I want to keep things short. Okay, the resized one would be to resize the NumPy array, which is BNA. Okay, to a size of 400 and 800, 480 times 480. So BNA 480 times 480. Okay, so two arguments for this MP resize. The first argument is the array to be resized. Okay, is the one-dimensional array to be resized. The second argument is the dimension. Notice that the second argument itself is a pair or is a two-tuple. Okay, so essentially it means that BNAR would be a 400 times 480 times 480 array with the content that is the same as the original one. Okay, so BNAR, I just want to try to check, is something like this. Okay, 480 element over there. If I want to look at its shape, then I just ask, okay, BNAR.shape, and it will tell me that it is 480 times 480. Okay, so up to this point, everything is fine. Any problem up to this point? I understand that there are a lot of things that you have to know about the packages, okay, the functions provided by the packages before you'll be able to go into coding. But well, this is the necessary evil. There are too many packages, too many functions, okay, and we have to try it, okay, one by one. And with the interactive environment, it's good that we'll be able to do it, okay, in a good way. Okay, we know that BNAR is a NumPy array itself, and so this BNAR is something that is read from the radar, from the mask. Okay, and so the question is, how can we write it to a file? How can we write it to a PNG file, for example? Again, earlier we read PNG file using OpenCV. That is the CV2 package under Python. So now, because we know that imread is the one to read the file, read the image file. So naturally, what do you think the name for the function name for the image writing should be? imwrite, yes. imwrite, this one. So imwrite is like this. Okay, imwrite is the file name, and then input array is the image, and then the parameters. Okay, so the file name, the image seems fine, and the parameters is something that has a default. Okay, notice that this is the C++ version of API documentation. Okay, we don't have a Python specific version, but still, okay, we can do a one-to-one mapping. The first one is string file name. The second one is the image itself, which is our BNAR. Okay, and so that's why I can do cv2.imwrite mask. It must be a string mask.png, and Is it the file name first? File name before the image. Okay, and the image is this BNAR stuff. Okay, and the next one I don't care about it, and I just enter, and I've done this writing, and it returned true, and it seems to be something good, and so I go back to the command line and look at it. Okay, I can see this mask.png. Okay, Firefox mask.png. Okay, and you get something like this. Wow, too bad. Completely dark. If it is a mask, okay, why is it completely dark? Then does it mean that okay, nothing in the image is worth processing? So we do a little bit of investigation. So this one, okay, I have to cut it. So 23 and 24. And why is this so dark? Okay, and I haven't really looked into the details of this BNAR array. And it's a lot of zero. Okay, I wonder whether it is always zero. Okay, and notice that okay, I can do max of 453, and I'll be able to do this. Okay, so given array, feed it into max function, I can see a max value, and so can I do max of BNAR? Okay, this is a two-dimensional array, and of course we cannot. Okay, we can only do a max of a one-dimensional array. So this is wrong. But I want to know whether there is any non-zero value over there, right? So there are actually a number of ways we can find out. Okay, since this is a NumPy array, okay, I can ask the question BNAR mp.org greater equals 0. Okay, I send it a query. Okay, this is the NumPy query. The NumPy query asks the question, okay, if all of them is equal to 0, the answer is no. Okay, and so there must be some non-zero values over there. And so mp max BNAR, okay, I don't know, okay, I'm not really that familiar with that, but I guess MP will give me this facility, and by a little bit of experimentation, I find that the maximum value of BNAR is 1. So it means that this is a bit, essentially a mask of either 0 or 1. Okay, so the question is, how can I make this 1 visible? Okay, I'm going to write it into a PNG file. The PNG file, if the grayscale is 0, then it's black. If it is 1, then it's a little bit less than black. Okay, what's the maximum value for a grayscale PNG? What is the maximum value for a pixel in a grayscale PNG that's 8-bit in depth? 255. Yeah, 8-bit. So the range must be 0 to 255. So I want to turn all the 1s into 255s. Okay? And so what I can do is actually to try it like this. BNAR. I directly write it into a file. Okay. So CV2 image write, IM write. Okay. Mask.png. And then it is BNAR, but I want every value to be multiplied by 255. So if it is 0, then it remains 0. If it is 1, then it becomes 255. So that way, after writing to the file, okay, I should be able to see the non-zero pixels. Okay, notice that I can do this. The reason is that this is a NumPy array or a NumPy matrix. A NumPy matrix does operations element by element. So BNL times 255 means that every element is multiplied by 255, and the result would be this object. Okay, this uh, uh, purple thing is a two-dimensional array whose value is either 0 or 255. Okay, true, good. Okay, and I look at the file, and now I can see the mask. Happy. I have the radar. I have the radar. I have the mask. I have the radar. I have the mask. I have the radar, and finally, what has been promulgated this morning is now clear. Remember earlier there in the morning, the observatory friends have said that there is some area in which the radar is blind because it's blocked by a building, and this area is this area, right? And so effectively, what is being shown here is the visualization of a mask as a PNG file, and also we know which part of the data is supposed to be meaningful. So the black part is actually not supposed to be meaningful. So look at area around here, okay, and the image, okay, the area around here is dark, and somehow maybe the radar find that, okay, the interpretation there may be some error, okay, in the interpretation to calculate the 3 km CAPI. Okay, so it's not very confident, and so the radar processor consider these pieces of data to be not safe. Okay, so it's masked out. Okay, so we have radar, we have the mask, and the next question is, how can we generate an image that contains only the masked, only the part of the radar with activity that has not been masked out? That is, I want to set the value of this picture. Okay, the value of the pixel of this picture to be 0 if the corresponding pixel of the mask is 0. Guess what we can do it. So essentially, we have two matrices. Okay, we have one matrix which is the radar matrix, another matrix which is the mask matrix. Okay, the radar matrix itself, okay, contains grayscale value from 0 to 255. Each of them can be interpreted as the Z value, which can be converted into R value. Okay, doesn't really matter to us for this exercise. And we have the mask value, and the mask value is either 0 or 1. And I want all the corresponding pixel of the image, of the reflectivity image, whose mask value is 0 to be 0, whose mask value is 1 to be unchanged. So how can we do it? So a little bit of an experiment first, okay. mp.array, mp.array, four, five, six, seven, okay. B this one, okay. So essentially, this is a, well, the image itself is a big version of this small thing. Okay, the question is, how can we generate an array which is 4007? Your guess. You don't need to understand Python, okay? Because it's not Python stuff. This is NumPy stuff. Yeah, do you write the loop or something? Or very simple expression indeed. A minus B times B. Yes. Okay. So we still have half an hour with the code here. Okay, can you write the program experiment? Okay, and generate the master image file. Most of them has been done for you. Okay, and generate a master image file and make it master.png or something. Okay, and you'll be able to compare the differences. So I walk around. Okay, hopefully be able to answer your questions, and I'll review the answer after 10 minutes. The code is here. Seems everyone is okay now, right? So the answer is very simple. I am right. Must.png, and this is BNAR times the original of relativity. The original relativity is IM. Okay, so IM times BNAR, BNAR times IM, the same. Okay, and so we look at the must.png as well. And we have this. Okay, so this is the mask itself. Okay, so this is the original data. This is the master version. Okay, much cleaner. And what you can notice is that this one we have low reflectivity areas over here, and all these low reflectivity areas have to be masked out. Only those speckles which are relatively strong in reflectivity remains. Okay. So this one, of course, you can save a notebook. If you save a notebook, then it become untitled.ivmb, and next time you'll be able to open it using Jupyter yourself. And of course, you can save notebook as another name. Okay, so maybe mass generation. Okay, mass radar. .ipymb. So to mask it, okay, it's like this. So next time you'll be able to try it out again. Okay, for example, I close it. Okay, and next time what I can do is to Jupyter, Jupyter lab, and then the mass radar .ipymb, and you will be running. You'll be looking at the Python notebook that way. Okay, directly. Okay. So it's a situation. And it's an interesting environment. Okay, nice environment for trying things out. And so Jupyter by itself, okay, will allow you to convert from one format to another and so on. And you can try it, okay, yourself for that. Okay, so any questions up to this point? You can keep the VM. Okay, the VM. What's special about VM is that it's installed with some of the packages. Okay, that may be useful, and it's also installed with NCL as well. Okay, and NCL, that is the Anchor command language. Okay, you can go to NCL Anchor command language. Okay, it's this one. It's installed with this one as well, but I haven't installed the shape files. Okay, to use it effectively to draw contours of seashores. Okay, and you have to install a few shape files, and I haven't installed the shape files for this package. And you can go to the right place and look up how you can install the shape files. It's essentially download a package and put it somewhere under the NCL home package, and you'll be able to draw pictures like this. Okay, in a very detailed way. Okay, it's a very nice one to try. And okay, so much for my talk today. Okay, any questions? Okay, the lecture notes will be available later. Okay, and so if you don't have questions, then I'll give the floor back to Dr. Ting.
Okay. So that's all, folks. Thanks for coming to this workshop, and I would like to remind you that please go back and try to create a Microsoft Teams account and send it to me so that I can add you to the chat room. And from say now on, then our communication will pretty much depend on the chat room. So everything that we want to announce and any question that you want to ask us are through this chat room. Okay. Any question that you want to ask before we dismiss ourselves? Okay, so that's very good. Thanks for coming. And let me the hackathon starts from October 12th, not 11th. Okay, sorry about that. Okay, so see you. Okay, for the closing ceremony, so we expect each group will give a 15 minutes presentation before the judges. Okay, so we have 10 group, so we expect we take 3 hours. So starting from the 9 o'clock and then to 12 o'clock. Okay, then of course after that, then we have lunch, and then the judge will look at it and discuss, and then find the winners, and then we will have the award presentation around 2 o'clock. Okay, so this is a preliminary tentative plan, and we will give you the final schedule. Okay, as soon as it is confirmed. Okay.
Yes, later. Yeah.
There's a PDF document.
The PDF document, yes.
We have one created. Okay, so maybe I'll put it in one part.
Yeah, the same folder.
Yeah, right.我可以申請到嘅，即係自己申請，你係要自己申請。其實就我唔係好熟 Microsoft，但係我Angus County 我 你哋試下先。
我自己試
如果出事